Right, okay, carrying on from the previous video about resonance, we're going to talk about what happens when we take energy out of a simple harmonic motion through one means or another. Could be air resistance. We're going to talk about damping. And there's not a huge amount to say about damping, really. Hopefully this video will be quite short, because the idea is that damping is just the removal of energy from a system. But there are some very specific kind of key terms that you need to be aware of in terms of what damping entails and what different types of damping looks like. Okay, so normally when we have something oscillating, simple harmonic motion, we would expect this. We would expect some sort of continuous amplitude, okay, without too much difficulty. However, in this case, damping creates a situation where we have a decreasing amplitude over time. So we have decreasing amplitude over time. So here we have starting out. I'm going to make an attempt to do this. Okay, so hopefully you're able to see there the effect of the damping causes a reduction to the amplitude because, and as we know from the equations of potential energy or total energy in a simple harmonic motion system, that it is reliant upon the amplitude, how much energy realistically is in the system. So, so in this case, we're reducing the energy in the system over slowly but surely, and as a result, we call this light damping. Now, actually, light damping can occur just generally over time on any pendulum because of air resistance, and so as a result, we get that reduction in amplitude because work is being done to the air particles to move them out of the way, and that energy henceforth is being transferred to heat, for example, in moving those particles around. So yeah, so we have this idea of light damping, but there are other forms of damping as well. There are two. One is a bit more substantial, and then the other one is even more substantial still. Apologies for my not straight lines here, but I'm sure you understand. So what happens if we have a heavier damping in a system? Well, we end up having something that looks like this. Okay, so heavier damping will cause the oscillations to die out much quicker. So we call this heavy or over damping. Heavy or over damping. And then finally, we have something called critical damping. Okay, so critical damping basically stops it in the shortest possible time. To be fair, actually, critical damping probably might not even get this much of an oscillation in. So critical damping would stop it. So we call this critical damping, which basically stops any oscillations really straight away. Now, damping has an effect not just on oscillations, but it also has an effect on resonance, because the effect of resonance is that we're increasing the amplitude. Well, if damping is acting to reduce the amplitude, if we damp a resonated system or a resonant system, then what ends up happening is we don't get either the resonance we want, or we don't get the amount of damping we want. So we have to look at it from the point of view of, okay, well, how much damping do I need? How much resonance do I need based on whatever circumstance you're looking for? So for example, in the destructive sense of resonance, if I want to avoid resonance, I add dampeners into the oscillating system to stop resonance from happening. And as a result, we kind of balance out the effects of the resonance when we know it's going to happen. And so as a result, we prevent any damage, which we can talk about more, and we'll have a look at some very specific examples in class. But so just to kind of summarize the idea that damping removes energy from a simple harmonic motion. And the idea is that which reduces the amplitude over time. So please just make some notes, make sure you have these diagrams. Please check in your textbooks just to make sure that you're happy with that, and you'll see some other graphs and things that we'll talk about in lesson as well.